The universe is a vast and mysterious place. One of the most intriguing discoveries of modern astronomy is that the universe is expanding. This discovery has revolutionized our view of the cosmos and raised profound questions about its origin and ultimate fate. The key to unlocking this mystery lies in a phenomenon known as redshift. Redshift is a subtle but profound effect observed in the light from distant galaxies. As light travels through space, the fabric of space itself expands, stretching the light waves. This stretching causes the light to shift towards the red end of the electromagnetic spectrum, hence the term redshift. Just as a siren sounds lower-pitched as it moves away from us, light from a receding galaxy appears redder. Redshift provides compelling evidence that these galaxies are moving away from us, and the greater their distance, the faster they recede. To comprehend the concept of redshift, let's draw a parallel with a familiar phenomenon, the Doppler effect. Imagine an ambulance rushing past you, its siren blaring. As the ambulance approaches, the sound waves are compressed, resulting in a higher pitch. Conversely, as the ambulance moves away, the sound waves are stretched, causing the pitch to lower. This change in pitch or frequency is the essence of the Doppler effect. In a similar fashion, light waves emitted by a galaxy moving away from us are stretched, resulting in a shift towards the red end of the spectrum, redshift. By carefully analyzing the redshift of light from distant galaxies, astronomers can determine their velocities and distances, providing crucial insights into the universe's expansion. The discovery of redshift in the light from distant galaxies was a pivotal moment in cosmology. It provided the first concrete evidence that the universe is not static and unchanging, but is, in fact, expanding. When astronomers observed the light from distant galaxies, they noticed a consistent pattern. The farther away a galaxy was, the more its light was redshifted. This implied that galaxies are not simply moving randomly through space. Instead, they are moving away from us, and the farther they are, the faster they are receding. Imagine dots on the surface of an expanding balloon. As the balloon inflates, the dots move farther apart, with the dots farther away seemingly moving faster. This analogy helps visualize the expansion of the universe, where galaxies are like the dots on the balloon, moving apart as the fabric of space itself expands. Wherever astronomers looked in the sky, they observed galaxies receding from us, painting a picture of a universe constantly expanding in all directions. The observation that galaxies are moving away from us, with their speed proportional to their distance, is not a random occurrence. It follows a specific relationship, now known as Hubble's Law, named after the astronomer Edwin Hubble, who first formulated it in 1929. Hubble's law states that the velocity of a galaxy is directly proportional to its distance from us. This relationship can be expressed as V equals h0d, where h0 is a constant of proportionality known as the Hubble constant. This simple yet profound equation tells us that the farther away a galaxy is, the faster it is moving away from us. Hubble's discovery revolutionized our understanding of the universe. It provided the first observational evidence for the expansion of the universe, confirming that the universe is not static, but is indeed expanding. The Hubble constant, denoted as h0, is a fundamental parameter in cosmology. It quantifies the rate at which the universe is expanding. Determining the precise value of the Hubble constant has been a major goal of observational astronomy for decades, as it holds the key to understanding the age, size, and fate of the universe. The Hubble constant is typically expressed in units of kilometers per second per megaparsec, or km/s/mpc. 1 megaparsec is equivalent to 3.26 million light-years. A Hubble constant of 70 km/s/mpc means that for every megaparsec farther away a galaxy is, it appears to be moving away from us 70 kilometers per second faster. Astronomers use various techniques, including observing type Ia supernovae and studying the fluctuations in the cosmic microwave background radiation, to refine our measurements of the Hubble constant. The current best estimate for the Hubble constant is around 73 km/s/mpc, although there are still some uncertainties and discrepancies between different measurement methods. The cosmic microwave background, or CMB radiation, is a faint afterglow of the Big Bang, the event that marked the beginning of our universe. It is a faint, uniform glow of microwave radiation that permeates all of space and is one of the most compelling pieces of evidence for the Big Bang theory. This radiation, discovered in 1965, provides a snapshot of the universe as it was just a couple of thousand years after the Big Bang. In the early universe, incredibly hot and dense, matter and energy were tightly coupled in a primordial soup. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, making the universe transparent to light. This event, known as recombination, released a flood of radiation that has been traveling through the universe ever since, gradually cooling and stretching as the universe expands. Today, we observe this radiation as the cosmic microwave background, with a temperature of about 2.7 Kelvin. The tiny temperature fluctuations in the CMB provide crucial information about the seeds of structure that eventually gave rise to galaxies and galaxy clusters. While the discovery of the expanding universe was groundbreaking, an even more perplexing observation emerged in the late 1990s. The universe's expansion is not slowing down as expected due to gravity. Instead, it is accelerating. This unexpected finding led to the proposition of a mysterious force called dark energy, which is thought to be responsible for this accelerated expansion. Dark energy is a hypothetical form of energy that permeates all of space and exerts a negative pressure, counteracting the gravitational pull of matter. Its existence is inferred from its gravitational effects, as it leaves no directly observable trace. Observations of distant supernovae, used as standard candles to measure cosmic distances, provided the first evidence for the accelerating expansion. These observations revealed that the supernovae were fainter than expected, suggesting they were farther away than they should be if the universe's expansion were slowing down. This unexpected finding implied that the expansion of the universe was speeding up over time. The discovery of dark energy has profound implications for our understanding of the universe, suggesting that its evolution is influenced by this mysterious force that makes up a significant portion of the universe's total energy density. The discovery of the expanding universe and the subsequent revelation of its accelerating expansion have raised profound questions about the ultimate fate of the cosmos. What will happen to the universe in the distant future? Will it continue to expand forever, or will it eventually collapse upon itself? The answer to this question depends on the interplay between the universe's expansion rate, the amount of matter and energy it contains, and the nature of dark energy. Currently, the most widely accepted model for the universe's fate is the Big Freeze scenario. In this scenario, the universe continues to expand indefinitely, driven by the repulsive force of dark energy. As the universe expands, galaxies will drift farther apart, and the average temperature of the cosmos will approach absolute zero. Stars will eventually exhaust their nuclear fuel, leaving behind a dark and desolate universe populated by black holes, neutron stars, and faint remnants of light from long-dead stars. Other possible scenarios, though less likely based on current observations, include the Big Crunch and the Big Rip. In the Big Crunch scenario, the expansion of the universe eventually reverses, and the universe collapses back in on itself, culminating in a singularity. The Big Rip scenario proposes that the expansion of the universe continues to accelerate at an ever-increasing rate, eventually ripping apart all matter, from galaxies to atoms, into its fundamental constituents. The discovery of the expanding universe, initially met with skepticism and debate, has become a cornerstone of modern cosmology. The redshift of light from distant galaxies, meticulously measured and analyzed, provides undeniable evidence that the universe is not static but is, in fact, expanding in all directions. Hubble's law, a simple yet profound relationship between a galaxy's distance and its recessional velocity, underpins our understanding of this expansion. The cosmic microwave background radiation, a faint afterglow of the Big Bang, offers a glimpse into the universe's infancy, revealing a hot, dense, and surprisingly homogeneous early universe. The tiny temperature fluctuations in the CMB provide crucial information about the seeds of structure that eventually evolved into the galaxies and galaxy clusters we observe today. The discovery that this expansion is accelerating, driven by the enigmatic force of dark energy, has added another layer of complexity and wonder to our cosmic perspective. As we continue to explore the cosmos, armed with ever more sophisticated telescopes and instruments, We are constantly refining our understanding of the universe's expansion and its implications. The journey of cosmic discovery is far from over. It is an ever-expanding frontier, beckoning us to explore the unknown and unravel the mysteries that lie hidden within the vast expanse of the cosmos.